First thing we're going to focus on today is just briefly reviewing derivatives, but in more than one dimension. And we're going to come back to this in more detail when we do vector derivatives. This is just to get a starting look at the gradient and kind of the background of where we want it to come from and how we want to justify it. And most of this, again, should be, I hope, a quick review. I don't go all the way back. If you don't remember what partial f of x is, partial f of y is, partial f of z is for a function f of x, y, z, you'll definitely want to review that. The simplest thing is it just tells us keep everything else constant and use the rules for derivatives. So functionally, to take them is straightforward. It's just like taking a regular derivative. It's a little more important to kind of understand at times what it means mathematically. But the definitions of them are the same and all of that. But the question is, okay, that'll give me the change of f in the x direction, the y direction, or the z direction. But I'm often interested in something more general than that. So how do we develop and build up the concept of a derivative for something more general? And the first thing we want to think about if we start at some point x naught, y naught, z naught, keep in mind we're moving to a point x, y, z. That's the basic idea of the derivative. And if we're going to be in 2 or 3 dimensional space, we're doing this along some direction. So let's call that direction u hat for now. And we have this vector u sub s that takes us between these two places. So I can write the vector u sub s as u hat times a quantity s, which is basically its length. And so I would have a I hat plus b j hat plus c k hat times s. And this right here is u hat. So the coefficients a, b, and c are going to make this a unit vector for me in the direction I'm going in. They give me basically the direction, right? If I just added I plus j plus k, that's a single direction. I want some arbitrary direction, and that it doesn't even necessarily have length of 1. And then s gives me the magnitude of this little displacement that I'm going to make. And by constructing it that way, the first thing I notice is a fairly simple relationship between x, y, z and z naught. Whoops, I don't know why I keep writing a for each of these. Between x, y, z, x, y naught, z naught, and so on. And so we're going to use this to compute our changes. And we're going to use our ideas of what we mean by a total change of f with respect to this magnitude s that we made, right? So we want to figure out, we're going to be taking a limit as s goes to 0, but how big is the change in f given this change in s in this direction that we're looking at? And whenever we have a total derivative like that, we basically use the chain rule. And I wanted to emphasize that. There are a lot of times and places in physics where we're going to convert between some total derivative and an expansion out in partial derivatives. And so you want to have that idea. And notice, again, as a mnemonic, we use the cancellations. So there's a lot of times where we want to use this total derivative. And for our mnemonic, we're using the cancellations, the dx's, the dy's, and the dz's. But it's basically just the chain rule. That's what it's telling us. Now, at this point, we can just actually work that out. Because we know what dx ds is. We know what dy ds is. And we know what dz ds is. So this becomes df dx times A plus df dy times B plus df dz times C. Now, at this point, notice the structure we have. A, B, and C are what? But more than constants. I put it back up on the screen. Yeah, so what would we call those? They are the what of U? Coefficients or components. What other expression do we know of that involves a sum of products and components? This looks like a dot product, just a projection. And so it's natural to think of the df dx, df dy, df dz as the components of a vector. And that is why we're motivated from this expression to define a vector operator. Whoops. Oh, actually, I was writing it correctly the first time. So it's the partial derivatives are the components of the vector, and so it's I hat d by dx, j hat d by dy, k hat d by dz. We have to be real careful. Ultimately, if we were to write this in other coordinates, you do want to get the order correct, because you don't want to take the derivative of the unit vector that's defining the operator. So that's why I put it I hat d by dx. For Cartesian coordinates, it doesn't matter because the unit vectors don't depend on anything. But in other components, for instance, we might have r hat d by dr plus theta hat 1 over r d by d theta plus z hat d by dz. So that would be cylindrical. And then you can get one for spherical. But now, this object is a vector, so the object grad acting on f is a vector. And I can dot that into u hat. That gives me the expression up above, which was my df ds. And so this allows me to think about how I'm going to take the derivative, the total derivative of a function, in some direction given by this s coordinate, and u hat is the direction that s is in. And so this goes back to the one quiz question I noticed where there was a little more people having incorrect answers. If I want the directional derivative, which we're going to show in a moment that this is, it's the projection of the gradient, not the projection of the divergence. For those of you who answered projection of the divergence, you need to think a little bit more, because is the divergence a vector or a scalar? Scalar. So can I project a scalar? No, and that's one of the key things I said yesterday. We want to keep track of where we use our language. We project vectors. We don't project scalars, and we don't, a matrix isn't a projection. Projection are between two vectors to give us a scalar. Okay? Once we've created this vector operator grad, we now can configure a lot of other derivatives. We can make the divergence, which we're going to come back to in detail. But as I just said, it's a scalar. It's the dot product between two vectors. We can create the curl, which is a vector, because it's a cross product. We can create more complicated things. We can create del squared f, the Laplacian, and that is del dot grad of f. So this is, notice because it's a dot product, this is a scalar. And this order does matter. You have to be careful, because when you're computing it in polar and cylindrical and spherical coordinates, doing it this way will matter, because you're going to be taking the gradient, the divergence of a gradient, and this will have, means you have to act on the basis vectors, because this will be a vector. So we'll see that later when we come back to these. Any questions on that so far? Again, I really want to emphasize the following two key points. So now let's think about a curve that's represented, the path that my function is. Right? So fxy is my curve now through space. And if I look at my curve, you know, my usual thing, and I take u hat to be the tangent at this point, you know, what we were just doing as we take a limit is approximating, we come close to the tangent. So we would be asking things like, you know, df ds is the limit as delta s goes to 0, where these are all my little delta s's. And one of the things that's important, okay, is along u, because, I mean along this curve, because the line is by definition f of x, y is a constant, delta f equals 0 along u. Right, along, in all the tangent directions, the change in f is 0. I want to make sure we understand here, because again, think about this for a second, right? F of x, y, right? Normally we would write a curve perhaps as y equals some function of just x. So I want you to make sure the notation is clear. We've written this as a parameterized kind of contour, if you think about it. So f of x, y is a function of two variables, but its line where it's constant is a single curve in space, which you could rewrite as y equals some function of x, if you want to think about the normal way. And as we move along that curve, the total change in f, by definition, is 0, because f of x, y is a constant. So that means, by definition, df ds, which equals, we just found, oops, the gradient of f dotted into u hat has to equal 0. And there's a lot of ideas here that come up a lot in the math of physics. One is this idea of recognizing when a total change is 0. You're going to be doing a lot of Lagrangian mechanics and classical mechanics, where we look at the action and we want to minimize it. And so when we're minimizing a function, the total variation is 0. And then you have to go figure out what all the partial derivatives are that lead up to that total variation. So here along a curve, the df ds by definition is going to be 0 along the curve. And we have a dot product or projection in there. And when we have a dot product or projection, what do we know? If the projection is 0, what do we know about the two vectors? They are orthogonal. And so this is the fundamental reason you have to remember that the gradient is perpendicular to the curve. And in higher dimensions, it's going to be perpendicular to surfaces. So the gradient of a function is perpendicular to the curves of constant value of the function. So if I do a contour plot, and this is why you've all probably used this somewhere, right? If I'm doing a contour map of something, which are curves of constant values, then the gradients are all perpendicular to those and give you the direction of maximum change, because you're either at a maximum or minimum change. Now, the other thing, so we'll often call the magnitude of the gradient of f the normal derivative, because it's the derivative in the direction normal to the curve. So that's an important term. And of course, if you have some generic direction s hat, then the gradient of f dotted into s hat is what we call the directional derivative. And it gives you the derivative in that direction. That's all I want to say about derivatives for now. We're going to come back to the divergence and curl and do it in more detail where we worry about the physics of it. But are there any questions on this? Again, I'm hoping this is review. It should be review. You may not have heard it in this exact terms, but you should have seen something very close to this in your calculus classes. We good?